in, we need to find the location for F1, where's the force acting on the gate. So also simple, we just 4.25, which is the value of HP minus 2.5, we get 1.75 meters. So that's the location for F1. And then the last one is moment acting on the gate. So simple also, we just use the formula of force times the direction. Yeah, so we use for the direction, we use location of F1. So force times 1.75, we got 229.15 kilonewton meter. So that's the moment acting on the gate for seawater side. All right, next part, freshwater. Same like before for the seawater side. So we just use all the same formula, same equation, but different value lah. So here's we have the water density, the G and H T. Same like before, H T stand for the depth of the centroid. So same before, we just minus, and yeah, we get the value for HT. And then next we got F. So I will label here F2 as the hydrostatic force acting on the gate for freshwater side. So same, we just use the formula rho GHA, plug in all the value, and then we got 66.43 kilonewton for F2. So next I see second moment of area. So yeah, we just use the same formula and plug in all the values. So we got 1.085 meter to the power 4 for IC. Next HP, yeah, same like before juga. We use same formula, HP, center of pressure. We plug in all the value IC sine square theta over AHC plus HC, and we got 2.327 meter for HP1 and HP2. And the next, same location of F2, we use same formula, and then we got 1.827 meter. And last part, what we call this, moment acting on the gate for freshwater side. So the direction of the moment is clockwise. So for the seawater, it the direction is anti-clockwise. So here we calculate the moment, use the same formula, force times the location, we got 1 to 1.37 kilonewton per meter. So from here we can conclude that since force 1 greater than force 2, the gate will open toward freshwater side. So that's for the F force. But if we look at the moment, same too. Moment acting on the gate at Stillwater side is also greater than moment acting on the gate for freshwater side. So the gate will open toward the freshwater side. So that's all for question one for the triangle shape. All right, for the question two, for the triangle shaped gate, so here's the solution. But first of all, let's analyze the question for question two. So, question 2 asking to us analyze and solve the required freshwater depth H for the hydrostatic force at B to be net zero. And next, the question asks what will happen to the gate? Use the depth of knowledge of fluid mechanics fundamental to solve this equation. So, from here is the solution. We have the hydrostatic force formula here, and we also have HC that stands for centroid depth. So first of all, let's find out our HC. So we just use the formula given. Yeah, here's the formula, and we got 4.278 meter. Yeah, meter. And next we find the A that stands for area of the triangle. So we just use plug in all the value and we got 3.125 meters square for the area of the triangle gate. And last, for the hydrostatic force, we just use the same formula, rho g h HA. We plug in R, G, H, and A to the formula, and we got 134.43 kilonewton. Alright, next we need to find the location of the force HP. Okay, so here's the HP formula. You can see here I times to the sine square theta over HA plus H. So since we still missing I information, so we need to find the IC first. So IC stands for second moment of area. So we need to find it first. So we just use this formula, moment of area formula, the as the equation given. So we just plug in all the value BH cube over 36 and we got 1.085. So next we can define the location of the force HP, plug in all the value and we get 4.339. So last we need to find the moment acting on the gate for the seawater side. So yeah, we just here just plug in all the value and as we can see here there's an extra information x. So what is x? So x is the distance along the gate, so we need to find the x also for our calculation here. Yeah, so uh pop up force times location, we got 23390.8.2 233,908.2 not Newton meter. So that's the moment acting on the gate for the seawater side, and the moment is on anti-clockwise direction. All right, so here's the next part for the freshwater side. So, same like before, we need to find the hydrostatic force using this formula. Okay, we just plug in all the value and. So since the question asking us to find the H, so in this calculation we need to put H as our unknown value. So yeah, we got this equation for the hydrostatic force equation, and then next HP. Yeah, HP. Yeah, you just use the same formula and same H we just put as a noun. So HC also the same. Got this, and for the inertia also since for IC there's no need of value h, so we just plug in everything and we got the value for IC 1.085 meter to the power 4. Okay, next. Sorry. Okay, next. Oh, moment. Okay, moment balance. So since the question said that the net moment is 0, so we can conclude that moment on seawater is equal to the moment summation of moment at fresh water. So we get this equation. So same like here too, we need to find x as the, yeah, like before lah, the location, the head. So yeah, we just do the same here. So this side we need to, like, we trying to find the moment acting on the gate for the freshwater side. So just use our mathematics skill, yeah, and plug everything and do the mathematics, and yeah, we get h equals to 5.12 meter. So in conclusion, since the actual freshwater level shown is only 3 meter and the required height to overturn the gate is 5.12 meter, and yeah, conclusion, the gate will not overturn. So that's
So as my teammates have already explained, I will just be showing the results of the circle-shaped gate. Okay, so as my teammates have already explained the workings of the problem, I will only be presenting the solution. As my teammates have already presented how the hydrostatic formula works, I will only be presenting the results of the circle-shaped gate. As you can see here, even though the method of finding the hydrostatic forces are the same, but the resultant forces are different. This is mainly due to the different shape of the gate and also the different moment of inertia of the gate. That's why we can get different values here. But if we look at question 2, the depth at which it is needed to open the gate from the freshwater side, it remains the same, 5.11 meter, consistent with the other questions.
For question 1, we calculated the hydrostatic force and moment acting on the trapezium-shaped flip gate from both the seawater and freshwater sides. First, we determine the area, centroid, and the center of pressure of the gate. Then we apply the hydrostatic force equation to both water levels. So the result show that the seawater exerts a force of 206.674 kN with a moment of 338.689 kN per meter, while the freshwater exerts 93.667 kN with a moment of 175.260 kN per meter. Since seawater is denser, it produces a greater forces and moment. For question 2, we determine the minimum freshwater depth required to prevent the trapezium-shaped gate from overturning. So using momentum equilibrium, we balance the moments caused by the seawater and freshwater acting on the gate. Our calculation shows that the required freshwater depth is 5.121 meters. Therefore, the gate remains stable and will not overturn under this condition.